We are back and we're going to do our Pset 5 solution video. So we have a cantilever beam, PVC pipe, so that means our Young's modulus is equal to 1 GPa. Applied load is this, beam is this long, 20 inches thick, so that's going to be our H base, so B, 3 feet. Strain gauges are placed 0.1 meters from the cantilever support. So here to here is 0.1 meters. The length of this, the total length, is equal to, 50 meters. 50, oops. The load is applied halfway from the length of the beam. So this is at basically L over 2. So my distance between where the load is applied and where the strain gauges are is just going to be L divided by 2 minus 0.1 meters. So we'll have to figure that out. That is equal to our D. Load applied. Excitation voltage is 2 volts when the load is applied. So my delta V naught is equal to 1 volt. My VI, or excitation, is going to be 2 volts. Write out the strain in each strain gauge. What's the gauge factor? So we're solving for the gauge factor. We know if I have my X and Y, so I'm going to assume that there is going to be, we know our relationship is delta V naught divided by VI equals F over 4, epsilon 1 minus epsilon 2 minus epsilon 3 plus epsilon 4 for the fourth strain gauge. So we know that if I bend, so if I'm doing bending, the second strain gauge is going to be equal to E bend, positive is going to extend. E3 is going to be equal to minus E bend. E4, as I bend and extends, it's going to be actually minus Poisson's ratio E bend, because it's actually shrinking, but it's not shrinking, proportionally, because again, it's going to be extending out here, so it's going to actually shrink here, where we're measuring essentially in that direction. And then E1 is going to be equal to positive nu EB, because it's going to be essentially compressing and it's going to be popping out. Excellent. So we figured out number 1. Now it's just solving essentially for the rest. So we know, for example, Y equals 1 times 10 to the 9th gigapascal. Nu is equal to 0.4. Nu is equal to 0.4. Del V naught equals 2. VI equals 2. There we go. 1 second here. So let's go ahead and define the rest of these values. E1, I'm just going to say, is equal to nu times EB. We're going to say, and actually we're going to find EB right now. So my strain of bending is going to be equal to 6 times the load, P, divided by Young's modulus times base times height squared. There we go. For that cantilever beam, actually times D, the distance, times D. And what we're going to do, load is applied, and that's an approximate. We're playing around a little bit, but anyways, you can do it even more rigorously as well for this, but you can utilize this expression. And actually, we can just treat it like a cantilever. But anyways, doesn't matter. So we know that here our length is equal to 50 meters. We know that our B is equal to 3 feet times 12 inches times 0.01254. Convert inches to meters. We know our H is equal to 20 times 0.01254. Let me make sure that 0254. Excuse me. I knew that something was wrong. 0254. Fantastic. I know that my D is going to be equal to L divided by 2 minus 0.1. And then excellent. So E2 is equal to EB. E3 equals minus EB. E4 equals minus nu times EB. There's no temperature information, so I'm just going to assume that that's not changing, so it's 0. And then what we're going to do, we have all those values set up, and I'm going to solve del V naught divided by VI set equal to F divided by 4 and then E1 minus E2 minus E3 plus E4. Solve for F. Whoops. What doesn't it like? We need to find our P. Our load, what was it? 1 kilonewton. Where are you? Yep, 1 kilonewton. 1 times 10. This is why I love Mathematica, because you can just see, oh, hey, this is not defined. Because it's blue. Ooh, what's going on here now? So let's see, what doesn't it like? What's going on here? Or what's going on here? Ooh, what do you know? We're canceling each other out. So, what a fun problem. It's a nonsensical one. So we could have skipped some steps. But, hey, that's the fun with these problems. Excellent. All right, so let's go to the next one. I always forgot. I knew that was one of those. Okay, I'm working with titanium alloy. Blah, blah, blah. Diameter this, thickness this. Typically a fraction of 30% strain. This. All strain gauges have resistance of 120 ohms. This has the shunt resistor is 100k ohms. Initially, when the switch is closed, my DAC reads 5 volts, and the gauge factor is 3.8. So we have, and we know when we're dealing with a shunt resistor, so my strain is going to be equal to the absolute value of minus 1 over F of R, which is just going to be the 120 ohms, over R plus R shunt, which is 120. So this is going to be the strain just when we close essentially that, basically that shunt and that switch. And does it say anything? When the switch is closed, my DAC reads 5 volts. Gauge factor is this. Right at the strain. What will be right before fracture? What will the DAC read? Okay. So we're gonna actually have to do basically a ratio here to figure it out. So we're gonna do this in a couple of different steps. So first, before we even get started, let's confirm, is this the thin wall pressure vessel? So I'm gonna go ahead and I'm going to actually quit this. There's quite a bit going on in this problem, but I love these problems because these are very realistic problems. So we're told titanium, so I'm going to say Y is equal to 100 times 10 to the 9th. My nu is equal to 0.3. Diameter, so my radius is equal to 50 times 10 to the minus 6. My thickness is equal to 3 times 10 to the minus 6. And a typically fracture at 30% strain. So let's go ahead. Right at the strain. Maximum pressure that it can withstand, and then right before fracture, what will the DAC read? Okay, so we're going to take it step by step by step. So first, are we a thin-walled pressure vessel? That's the question. Is R over T greater than 10? Oops, let's see, go back. It was blue. Blue. You're charging me for blue. That's a very... If one of you can tell me that reference, I'll give you extra credit somehow in the comment section. Blue, you're charging for blue. Anyways, let's let this run. Let's assume that we are going to be in a thin wall pressure vessel. That means our one direction is our hoop, our two direction is our longitudinal. So if I'm writing out epsilon 1 minus epsilon 2 minus epsilon 3 plus epsilon 4, I am going to, or we are going to kind of see that effectively we're going to calculate this is 0, 1 2 3 is 0, so epsilon 2 is equal to epsilon h, which is equal to 1 over e times sigma hoop minus nu sigma l. Our epsilon 4, back or front doesn't matter, that's still equal to epsilon l, which is 1 over e sigma l minus nu sigma h, where sigma h is equal to delta p r over t, sigma l is equal to delta p r over 2t. So what we're going to do here, r over t is greater than 10. So yes, we can make the thin wall assumption. We wrote out the strain in each strain gauges, which is great. What's the maximum amount of pressure that these synthetic arteries can withstand? So we're told that strain failure is equal to 30%, so 0.3. So let's go ahead and let's say we also know that sig h equals del P times R over T. My sig L is equal to sig H divided by 2. We're also told that EH, I'm going to say equation 1 is EH, which is equal to, actually, I'm just going to keep those. Yeah, I'm just going to say EH equals 1 divided by Y, sig H minus nu times sig L. And then I'm going to say EL equals 1 divided by Y, sig L minus nu times sig H. Great. So we are told, so it's always, our thin wall pressure vessels will always fail in the hoop direction. So when this is equal to E failure, what was our delta P? So this would be the maximum pressure that can be withstood. So if I get this, so that would be my del P. So then this would be my EH, this would be my EL, et cetera, et cetera. So we have those. And we also know that E1, I'm going to say, actually, let's define it. Let's define it there. We know that E2 equals EH and E4 equals EL. Excellent. So what right before fracture, what will my DAC read? So we have essentially the strains. So when we just touch the switch, this is where we actually have to go back a little bit. So my E shunt is going to be equal to, and our gauge factor here is what? I think it's at 3.8. Yeah. So I'm going to say F equals 3.8. So when we close, E shunt, when I just close it, it is going to be absolute value of minus 1 divided by F times 120 divided by 120 plus 100K. So that's going to be the strain in the shunt. So that's E shunt. So V shunt, my voltage was equal to what? 5 volts. 5 volts. So that's the strain measured by the shunt. Now, if I am in this configuration of my Wheatstone bridge, it is going to be now this ratio. So now the strain that is measured, so like this is the voltage that correlates to this E shunt value. Now, I'm going to do my basically E1 plus E2 plus E3, all that good stuff. So now E wheat is just going to be minus E2 plus E4 in that configuration. So now that's going to be, where is it? Basically, right here. Well, it's going to be E2 plus E4. So what we're going to do now is we're going to do a ratio. And remember, because actually if you don't do the absolute value, I think this is also negative. Yeah, so it's just, we're looking at absolute values here. Yes, so E1 plus that. So now what I can do is just a ratio. So if I do, for example, solve E wheat divided by E shunt, set it equal to V wheat divided by V shunt. And then we see a much larger value, which is kind of what we expected. So there you go. That's how we do that one. So let's look at the next problem. So what we're going to have to do here, now we're dealing with a ceramic. So let's go ahead, let's quit this out here. Good. Tungsten, a ceramic. Bending will push the sheet out of the page. Compressive stress here is 10 kilopascal. Shunt resistor is this. The gauges all have resistance of 500 ohms. Gauge factor is 15. Excitation voltage is this. Complex rotating state, the DAC reads. So this is my delta. So my delta V naught is equal to 15 volts. My VI is equal to 5 times 10 to the minus 3 volts. My F is equal to 15. We all have equal resistance. We're not turning or basically closing the shunt this time, so that's just kind of a kind of a false piece of information. There's no stress in the 1,1, so that's 0. There is a stress in the 2,2, and that is negative, and that is compressive minus 10 kPa. So voltage at balance, prove this, I mean, again, they're all resistances are equal. You can do that in your notes. So output voltage should be 0. Full expression of the strain measure. So let's look at our strain. Our strain in the 1, 1 direction is going to be equal to 1 over E times, now there is no sigma 1, so it's just going to be minus nu sig 2, 2. My strain in the 2, 2 will just be equal to 1 over E, and I'm just doing this shorthand here because I know that sig 1, 1, sig 3, 3 is 0. Now there's also a bending. So there's a bending stress, essentially, that is occurring here as well. So we have to kind of consider that. We're at the strain. Actually, yeah, we can solve for that bending strain, yeah. So let's go ahead and write out for each kind of direction. So if I'm looking at my strain gauge E1, epsilon 1, I have, and it's, again, this is all these other values are known. I'm going to be measuring the strain in the 1 direction, so E11, and then when I'm popping out of the board, it's going to be plus E bend. If I'm looking at E2, I'm going to be measuring the strain, and I'm going to kind of change, I'm going to change my notation. No, I'm not going to change my notation here. The only thing I'm going to change is I was measuring this. This was, here. That's strain in the 2, 2. This is measuring strain in 1, 1. And then because I am basically bending out and it's popping out, it's going to be minus nu EB. E3, which is on the bottom now, is going to still measure the strain in the 2, 2. But now because I am bending out, that is compressing. So that is going to be minus EB. And then finally, E4 is going to be equal to, as I bend out, let me see, pops out. So as I bend there, yeah, it's going to be, I'm measuring E22 plus nu EB. Excellent. So that is fantastic. So we've got all the strains here. We have essentially all these definitions. Now it's really kind of time to solve. And we can get this. So y is equal to 300 times 10 to the 9th. My nu is equal to 0.2. My strain, my gauge factor F is equal to 15. My del V naught is equal to 15. My VI is equal to 5 times 10 to the minus 3. Let's see here. Sig 2, 2 is equal to minus 10 times 10 to the 3. I think, let's do E11 is equal to basically 1 divided by y, sig minus nu times sig 2, 2. My E22 is equal to, I'm just going to drag this over a bit more. And when I say a bit more, I mean quite a bit more. Great. E22 is equal to 1 divided by y times sig 2, 2. We're also told, or E1 is equal to E22 plus EB. My E2 is equal to E11 minus nu times EB. My E3 is equal to E22 minus EB. And then E4 is equal to E22 plus nu times EB. All right, and then we also know we're going to solve, actually let's solve it later. So let's go ahead and solve for the bending strain first. So I'm going to say solve del V naught divided by VI equals F, or double equals F divided by 4 times E1 minus E2 minus E3 plus E4. EB is that, which is pretty large, but it is what it is. So we'll define that. That's our strain of bending in this crazy problem. It just kind of makes sense. I mean, again, it's ridiculous, but that's a big output voltage. But anyways, E1, E2, E3, E4, E5, and that one, or no, there's no E5. Fantastic. All right, last problem. Plated a delta strain rosette on a ceramic material, obtained strains in arm A, B, and C respectively of this, this, and this. Write out the principal stress and strain states. We're going to actually ignore the principal stress states. You can do those, but we're not really that interested in it. Do it for fun if you want. We will do it the principal strain states and a rotation to get to those states. We're using a delta rosette, so that means we have, for example, A, B, and C. Those are 60, and then this angle is 120, respectively. So A is, so if I draw our strain, I draw this divided by 2. So our A is 183, our B is 60, and then this is 10 microstrain. All right, so I like this because I like to kind of look in this direction. So we're going to do here, and we're going to calculate C. We need our R, wherever this is here, R, and we need this angle 2 theta. So I'm going to orient my system as such. So let's go ahead, and I'm going to say, so we're going to say, for example, EA equals 183 times 10 to the minus 6. Oops, 10 to the minus 6. EB is equal to 60 times 10 to the minus 6. And EC is equal to 10 times 10 to the minus 6. And now what we're going to do is we're going to solve. So we know our first expression will just be EA, set it equal to C plus R times cosine of 2 theta. And then we're going to set it in degree. And actually, we're going to set this as E1. E1 equals this. That's good. And we're going to set that as 2. We're going to set that as B. And then we're going to do plus. Now it's 120 degree. And then finally, we're going to do equation 3. That's going to be EC. And then it's going to be 240. Great. And now we're going to solve. Solve. 3 equations, 3 unknowns. We're going to solve for E1, E2, E3. Give us those values. Let's look at it numerically. Let's pick the values that are actually, oops. That's the nice part. We can actually just reset this. And oops, let me get back over here. And there we go. Here's our C, here's our R, and then we can actually even pull out our theta. Now it's very interesting, our 2 theta. It's -8, so that means negative, remember, is, oh, it's actually clockwise. If we set up our center there, our radius, so it's actually, we're looking at, it's going to calculate the angle kind of going down here. So that'd be a clockwise angle. So we're actually looking at the distance, basically this theta here. But anyways, you kind of get the picture. So we've got our angles. If we want to calculate, now that we have C and R, if we want our principal strains, so C is equal to this, R is equal to this, and then, so E1 will be C plus, that's a good joke, C minus R, and voila, we got it. So actually, even the way we drew it is actually the circle ends are actually extending past it, but that's fantastic. So we'll see you in the next video, and good luck on your exam. Thanks. Bye.